Hello everyone, and welcome to Asking ChatGPT about future space technology. Now let me make something quite clear. I don't think it's necessarily a great idea to ask a large language model about anything critical, but fortunately this is not anything critical. This is me doing research for fiction. So I'm going to be making stuff up anyway, and given that I'm going to be making stuff up, I just want it to be semi-realistic. This is hard sci-fi. I'm aiming for more casual hard sci-fi. I don't want to dump all this technical information in front of the reader. I'm going for more space casual is what I call it. And all this stuff is going to be in the appendix. You know, it's like a Tolkien thing, J.R.R. Tolkien with Lord of the Rings. All the technical details will be in the appendix and not something that I'm going to bother the reader about. So this is not going to be super duper important. It'll just sort of be sprinkled in the general flow of things. So, but I still need to know it, right? Because it's my knowing it makes the story work. And so I started asking ChatGPT some questions. I'm not going to rely on ChatGPT. This is like the first step. And then I'm going to be talking to you about other sources like atomic rockets and actual papers, and we're going to discuss all of these technologies in greater detail. But I thought it would be amusing to get our start on these technologies by asking ChatGPT. So, what are the necessary technologies we need to develop to create nuclear saltwater rocket engines? So, nuclear saltwater rocket engines, as ChatGPT correctly explains, is one of the boldest and most extreme concept in propulsion technology. They're really pushing the fission thing to the limit, and it was proposed by physicist Robert Zubrin, who is famous for the case for Mars, and uses a solution of fissile material like uranium tetrafluoride in water as both fuel and propellant. Well, yeah. With nuclear reactor, what it means is the nuclear fuel, the reactive fuel in a nuclear reaction, as well as the propellant. Okay, with nuclear reactions occurring continuously as the exhaust leaves the nozzle. This is important. This is a wacky idea, the nuclear saltwater rocket. Basically, the reaction occurs right at the edge of the nozzle, so that you're not having to have this huge heat shielding thing, on the back end. I mean, it's still got to be pushing on the vehicle, but it reduces the stress on everything and heat shielding requirements if you have it do its reaction right on the edge there. But anyway, what it says we need to develop is fissile fuel handling and storage, highly enriched uranium or plutonium safely in high concentrations without initiating premature criticality. Quite right. And I don't know about subcritical geometries, but okay. I mean, see, this is one of those technical terms that sci-fi writer might sprinkle in if they need to, if they have people trying to develop this sort of form of propulsion and discussing it. And then we have advanced neutron control and shielding, definitely. This is basically the radiation shielding. The neutrons are a particular problem. So keep the rocket subcritical until the salt water is ejected, then allow criticality in the exhaust. So this is the trick with this kind of engine. High temperature radiation resistant materials. It still has temperatures exceeding 25,000 Kelvin, which most things, nothing, I don't want to say nothing, but nothing I know of can handle that. So we're going to have to be doing regenerative cooling, as it says. So it's doing a pretty good job here. Controlled flow-induced criticality. Yes, that's the part where we're making sure that it only goes critical at the right time and not exploding inside the ship. Very important. So free-flowing exhaust without melting or exploding inside the ship. Flow rate regulation systems. So these are things that are going to be developed in order to make this work out. But what I'm most interested in is if we're going to develop these things, the people developing each of these things, what else are they going to be working on? Like before they get to the nuclear saltwater rocket engine, which is, technically difficult. If they've already been working on some neutron control and shielding, then they could have been doing that for some previous fission system, right? So we get companies that are doing this thing and then that thing and then this thing. And then, well, this one is just for the NSWR. So that's a peculiar thing. So there are certain elements like fissile fuel handling and storage that are going to be for general purposes for fission. And then there's going to be certain things that are very specific to this particular kind of fission engine. So extreme radiation shielding for crew and electronics, well, that's going to be for a lot of different types of fission engine or even fusion engines. So we have that. And then remote or autonomous operation. NSWRs may be too dangerous for crewed proximity, probably. And that would save us from some of the other shielding, right? Especially for radiation shielding for crew and electronics. So it makes a good point here. And so actually in my timeline, in my future history timeline, the NSWRs are not used for crewed vehicles. They are used, well, at least except for one extreme example, but they're used for probe vehicles. And framework for using, and then there's the whole regulatory and safety protocols. Well, you could have a whole storyline where people are dealing with the safety protocols and regulations and stuff like that. But anyway, a short storyline, hopefully. Anyway, and then it actually assesses, you saw my question, right? It was just one line, but it does a very good job. It assesses the readiness of each of these things. The fissile salt solution chemistry, low. Neutron control and dynamic flow, very low. It doesn't actually assess, I mean, reactor, rocket, hybrid design might be, but it you know that it had 8 points up here, but it only addressed 6 of the technology areas, and it doesn't seem to have addressed the controlled flow induced criticality, which is the most important thing, and basically that readiness is none. So yeah, in short, the NSWR is a theoretically sound but massively difficult concept. It's like strapping a nuclear bomb to a fire hose and hoping it only explodes in the right direction. That's a very good description, but we would much rather than rely on ChatGPT here to get where it got that information from. And so that's why we're going to be going to atomic rockets and some papers, not just on the NSWR, but for other concepts that I'm going to take a look at. So, but it does a pretty good job of the summary. We wish that it would maybe provide its sources, and there are other large language models that provide sources, but then they sort of provide fake sources. So sometimes they're real sources, sometimes they're fake sources. Here's a speculative development timeline for nuclear saltwater rockets. I wanted it asked if I wanted a speculative timeline. I said, yeah, go ahead. And so it's got a whole research and development timeline, which I didn't use. But I might use in my future history. So at some point in my future history, which is a very long document already, it's more than 70 pages at the moment, and it'll get longer. I might throw this in. Right now I just have a mention of when they start actually using the NSWRs. So then it makes another suggestion, but I want to move on to something else. Another concept is the nuclear light bulb, closed cycle gas core engine. How difficult is that compared to the NSWR? What are the necessary technologies for it, and where do those technologies overlap? So this is a very apt thing. Again, like I said, which companies will be developing, working on one first and then the other, that kind of thing. It's called a light bulb because it contains superheated gaseous uranium plasma, 25,000 Kelvin. Don't trust it on the numbers. I mean, it's probably, but generally it sort of fudges the numbers quite a lot, and it depends on where it gets them from. Inside a quartz or fused silica pressure vessel. It's good, very good with words, but sometimes with the numbers, it's just making them up. The uranium doesn't mix with propellant, unlike NSWR, so that's important. We're not actually releasing the nuclear fuel. So we're always going to distinguish the nuclear fuel from the propellant. In this case, the nuclear fuel stays in, and the propellant is hydrogen, which goes out. And so the nuclear fuel does not get mixed with the hydrogen. and instead radiates energy through the quartz. So the nuclear fuel is contained in quartz, and then the heat is released through the quartz to the hydrogen. I don't know, I guess quartz is okay with conducting this heat. So we've got that risk of criticality explosion very high for NSWR because it literally is a criticality explosion, and low for the nuclear light bulb. Nuclear energy complexity very high. Radiation shielding needed extreme high. Materials requirement extreme very high. And political regulatory hurdles severe high. This is all correct. Crude mission compatibility low and less remote, which is a very interesting idea. And medium to high for nuclear light bulb. In fact, probably you wouldn't use a nuclear light bulb unless you had crew. If you didn't have crew, you would probably be using ion engines. And so yeah, tech development roadmap, because again, the specific impulse is 1,500 to 3,000. Ion engines can beat that. So you wouldn't need the nuclear light bulb unless you had crew. Tech development roadmap, uncharted, difficult but clearer. I do like that. It's got good phrasing on some of these assessments. The nuclear light bulb is safer, more containable, and conceptually closer to reality, but it still pushes the limits of material science and reactor engineering. Quite right. Technologies needed for nuclear light bulb, transparent high temperature pressure vessels. Yep. So the silica quartz, and gaseous fission core. So we've got this gaseous uranium hexafluoride. Basic gaseous core reactors were studied in the 1960s, but never flight ready. So that's a very good assessment. Hydrogen propellant heat transfer. Hydrogen must absorb radiated heat efficiently from the fission plasma through the pressure vessels. We haven't actually tested that yet. And there is some theoretical models that say that we don't really get that much and we get closer to the 1,500 instead of the 3,000, in which case it's not really worth it. We would just use NERVA if that's going to be how it is. Neutron and gamma shielding, neutron absorbers, gamma shielding. This shielding is mainly because it's still a reactor, and so there's still that worry, but it's at least not ejecting out the nuclear fuel. Plasma flow instability, or allowing criticality for that matter. Plasma flow stability and fuel recycling. So it doesn't try to confine fuel. NSWR is not trying to confine fuel. This one does. So then it needs to be careful. And then fuel recycling is a problem because NSWR, the nuclear fuel, can be replenished. These quartz crystals that are containing the fuel in the nuclear light bulb, that's a little bit harder to replenish. Reactor startup and control, as typical. I don't even know how to start up a reactor that is quartz crystals containing gaseous nuclear fuel. Anyway, no radioactive exhaust. Yes, good. Controllable and throttleable, if you say so. See, I'll trust it on that one. I have no idea. Potentially, I mean, it should be that the NSWR is controllable and throttleable. Potentially, well, maybe it only has a set throttle because you need the criticality. So, more politically and legally acceptable. Transparent materials don't exist that meet all the requirements. Thermal stresses on the light bulb walls is immense. Needs experimental reactors that have never been built. So, radiation shielding critical, nuclear light bulb also critical. Fissile fuel handling, sure, of course it needs them. And note that still uses uranium hexafluoride for both of them. I don't know if that's really what would be ideal for the NSWR. Nuclear salt water, exactly how that works, I'm not sure. High temp materials, nozzle tanks, containment vessel, neutron control, criticality timing, yeah, that in other words, having criticality right at the edge, and then moderator geometry is important there, and then autonomous ops. Well, we're not expecting autonomous ops for the nuclear light bulb, so we're gonna have to deal with that. While NSWR is like riding a controlled nuclear detonation, nuclear light bulb is more like building a miniature glowing sun in a jar. It's a good thing, and it probably got it from somewhere else. It's vastly safer, but still extremely hard. However, I have to say that generally looking at papers on these topics, or atomic rockets even, the colorfulness of the prose is not necessarily great. So actually, ChatGPT might make a lot of this sound a little bit more colorful than some of the other sources. It's vastly safer, but still extremely hard. ChatGPT is certainly more accessible than some of the other sources, especially if we're talking about scientific papers. It is insanely powerful and dangerous, brilliant but delicate. Okay? So, what concepts are more immediately viable than NSWR or nuclear light bulb, but offer better specific impulse than chemical or NERVA type engines and more comparable to ion engines? So, that is the real rub, right? What can compete with the ion engines is really what I'm saying here. So, more feasible than that, yeah, higher specific impulse, but not as low thrust. I didn't really ask about thrust, to be honest. So it's adding a condition here that I didn't really ask for. So nuclear electric propulsion with Hall ion thrusters. So the first thing that it throws out is actually something that it was supposed to exclude, right? It's more, this is supposed to be beating ion engines, really. But then it gives me ion engines first. Thrust very low. So it didn't even meet its own criteria that it specified right there. So sometimes it has this. And yeah, kilopower, the NASA's SNAP and kilopower are not actually really aiming to power these, I don't think. The SNAP, SNAP is old. Kilopower is meant to power surface bases, not really the Hall ion thrusters. If you're only at that level, you might as well be using solar panels. Reactors that would really beat the solar panels would be more powerful than kilopower generally, but we're talking about 100 kilowatts would be right around there. So kilopower I generally think of as trying to power bases on the moon, especially on the nighttime side. So Vasmir, which of course I ultimately adopted, but has problems. So it is a compromise. It can get. I eventually have hydrogen ones that do get 12,000 seconds. So and actively being developed. Ad Astra creates a branch in my timeline because Ad Astra is U.S. based, but my future history timeline is based on a consortium of countries known as TIPA. And that consortium does not include the United States. So Ad Astra makes a branch office in Mexico in order to get TIPA money, basically. So power source needs megawatts. See, I mean, that's what we're really aiming for. So we need a megawatt reactor, and then if we have a megawatt reactor, we need the nuclear stuff. And so it ends up being a chain reaction in development. And that's what is reflected in my timeline. But a lot of this other stuff is, I'm not sure about. Pulsed fission fusion hybrids. What I asked for was more immediately viable than NSWR or nuclear light bulbs. So it's really hoping on the fission, MIT's fission fragment rocket. And actually, the fission fragment wouldn't be fusion hybrid. I mean, it wouldn't be a pulsed fission fusion hybrid. It would be a fission fragment. That it would be, but let's say it's a fission fusion hybrid fragment. It would still probably get better ISP in the top end. Thrust low to moderate, no full prototypes. Yeah, no kidding. Components being studied, yeah. Ultra high ISP, much more efficient than ion engines. I guess it's a good argument to be made that fission fragment engines are actually more viable than NSWR or nuclear light bulb. That's quite possible. I don't know. Viewers, you can give your opinion on that if you're knowledgeable about these futuristic things. But yeah, middle road between futuristic and feasible. But here, the ChatGPT is really helping out. For me to assess all these things, the reason why, people talk about the energy consumption of ChatGPT, but for each of these little requests of mine, it's giving a lot of information that I would take a long time and a lot of searching on the internet to gather together, right? Ultimately, I'll be looking at other sources, but this is a pretty good summary of some of the options, and some of them I might not have thought of, right? Of course, because I have used the Far Future mod and Kerbal Space Program and stuff like that, or KSP Interstellar, I sort of have a list of these in there because we have those parts, right? We have the fission fragment rockets, we have the Vasimir, we have the nuclear electric propulsion. So I have that available to me, but whether those numbers matched anything in reality, it's good to have verification for, and nothing about those parts in Kerbal Space Program gave me any sense of how those things actually worked, whereas this is helping me understand some of that potentially. So closed cycle gas core nuclear thermal rocket. That's the nuclear light bulb. It's still the nuclear light bulb. I asked for something, but here ChatGPT is failing. But it's failing. Let me explain the reason why it's failing. The reason why it's failing here, and it gives me ion thrusters as well as nuclear light bulbs when I specifically ask for stuff that is more viable than nuclear light bulb, and I already know about ion engines, don't bother with it, is because it wants a list of 5 at least. It just viscerally needs a list of a certain number, and it couldn't find those. So it had 1, 2, 3 really, and so it threw in some of the ones that were supposed to be already dealt with. So anyway, we do have the nuclear light bulb being mentioned here. And then rotating detonation engines, nuclear augmented rotating detonation engines. That I don't know if it's a thing. I like the little icons it has for them. Here it has a little icon indicating rotation. That's cute. That's cute. But I don't know if any coupling with nuclear is conceptual. I've never even heard of that. I've tried to find it. I haven't found anybody discussing a rotating detonation engine in particular, which is nuclear augmented. What I have found was that centrifugal, somebody introduced me to, was the centrifugal nuclear thermal rocket. But that's very different from a rotating detonation engine, because there's no combustion, right? Where's the combustion in a nuclear thermal engine? There's no combustion. You're passing the the propellant through the nuclear fuel, not actually, in contact with nuclear fuel. You're passing the propellant through the reactor and getting heat from the reactor to excite the little molecules so that they move faster. That's how you do it. But there's no combustion in a normal nuclear thermal engine. And so what is detonating in this rotating detonation engine? We're not too sure about that one. So there's really only 2 good ones here, Vasimir and the fission fragment rockets. But it was a tough question. What is more immediately viable that can compete with ion engines is a very difficult question. And probably the answer is nothing. But yeah. Recommendation, Vasimir and NEP are the top near-term choices. Yep, pretty much. For anything beyond Mars with speed in mind, fission fragment or hybrid systems. Okay, what developments would we need for Vasimir? Well, that's a good question, if I do say so myself. High-power, space-qualified energy sources. Yeah, so this ends up being one of the critical things. Nuclear power systems in the 500 kilowatt to 5 megawatt range. So that is, in my timeline, one of the first developments, along with advanced thermal management with the radiators and zero boil-off tanks, and robust plasma confinement and exhaust handling. So, well, that we already have with the lab prototypes with VX200, so I'm just relying on that. And integrated end-to-end system demonstration. That just means it has to be flown in space, so that's not a mission integration and control. These here again, these 2 aren't really about technological developments as such. They're just the end product of technological developments, and so it's trying to get 5 points here. It's trying to force that when it only has 3. It's like when, high schoolers are trying to find what to write in their 3rd paragraph in the normal 5-paragraph essay structure. You have the intro, you have the 3 paragraphs with the actual arguments and then the conclusion, and then they really only have 2 points, and then they try to fudge the 3rd paragraph. That's what we're getting here. So it's a very human sort of situation, but often ChatGPT really needs to be told, you don't need the extra points if you don't got them. So that's what we've got here. And it has a bonus fuel supply and storage. Actually, you should probably have moved that up. Especially with the hydrogen, you could have mentioned that a little bit better. Okay, and then it has a speculative timeline, which is fun. So then I really start getting into the meat of what I want. So what I wanted was I'm going to be making a future history, right? So now I have an integrated timeline for the use of NEP, Vasimir, closed cycle, gas core, that's the nuclear light bulb, that's not a separate thing. And NSWR that takes into consideration the enabling technologies for each and those, and when those will be developed. So we see a earlier nuclear electric and Vasimir era that's very optimistic. And then a mature NEP, advanced Vasimir early gas core experiments, which is probably also optimistic. And then we have this era, but it does, specify the milestones and events, closed cycle gas core prototype with 2000 plus ISP in 2055. That's not too bad. Simulated NSWR by 2065. That's also quite reasonable. So it creates a very rational sort of timeline, including the interstellar probe version of the NSWR, which Robert Zubrin actually proposed. How the nuclear saltwater engine can get 9,000 seconds of ISP, really. And then there's this interstellar probe one that gets 400,000. I have no idea how it makes that difference, and nowhere did ChatGPT explain that. But I think the main thing is more highly enriched uranium is what's going on with that, but I don't know exactly because we'll have to look at papers and such to figure that one out. So, NSWR remains a special purpose engine, too dangerous near Earth, but viable for high-speed robotic missions to the Kuiper Belt and beyond. So, its assessment there is correct. It doesn't create a bad timeline. It's not exactly the timeline I adopt. But it has a good table here, 500 kilowatt nuclear reactors, 1 megawatt nuclear reactors, cargo-ready Mars tug. So, and then Mars missions for nuclear light bulb in 2070 is a little bit late, but possibly mainstream here. So, overall, it's a very good timeline. And if people are interested in me talking more about this, I'll continue going. I've asked a lot of questions. We'll continue with this in a subsequent video to see what ChatGPT has and as answers for other things. So I continue on, and I'll be willing to discuss my investigation of these topics with you, and that's if people are interested. So it's up to you folks. If I get the sense that you're interested, I'll continue. But for now, it's a reasonably sized video, so I will say thank you for watching. I hope you enjoyed this video. If you did, please do press like. If you have any comments or suggestions, please leave them in the comment section below, and I'll see you next time.